Chapter 37 Interference of Light Waves. We have studied geometric optics in the previous two chapters. In geometric optics, we ignore the fact that light is actually an electromagnetic wave. We ignore the wave nature of light. We simply use the fact that the wavefront of light propagates in a direction that is described by a light ray, and then we look at how a light ray is bent upon entering the boundary between two different media, and then you can discuss what happens when there is a reflection or refraction at the border between two media, and then we have all kinds of results obtained from geometric optics that way. So basically we focus on light rays. We do not look at the wavelengths or the frequency of light. Okay, but under the right circumstances, the wave nature of light becomes prominent, and in that case the frequency or the wavelengths of light would make a difference. When we consider the wave nature of light, we will study what's called physical optics. Okay, so this is another branch of optics. It's called physical optics, in which the wave nature of light becomes important. Now, in particular, in the next two chapters, these are, by the way, the last two chapters of Physics 1C. Okay, chapter 37 and 38, we're going to focus on the physical optics. In particular, in chapter 27, we're going to study what's called interference, and in chapter 28, we're going to study what's called diffraction and polarization. Okay, now first of all, I want to tell you in a nutshell that there is only a technical difference between interference and diffraction. In both cases, what we're doing basically is use the so-called superposition principle. You know what that is, right? The superposition principle to add different waves together. Okay, the difference between interference and diffraction is the difference in the sources involved in the superposition. Okay, in the case of interference, I have discrete sources, say source number 1, source number 2, source number 3. Okay, they're discrete, they are numerable. You can count them 1, 2, 3, 4. In the case of diffraction, the source is a continuous source. For example, a slit with a certain size opening, and the slit has a certain width, which is not that small, so that you can think of the slit as made of infinitesimally narrow segments. How many narrow segments do we have? Infinite numbers. Okay, so in that case, when you add contribution from these infinitesimal segments up, you actually have to use the summation over infinitesimally small quantities. That, of course, is called integration, right? So that is the case of diffraction, where the source is continuous, and to add the contribution of the continuous source together, we have to use integration. Okay, but in any case, we have to use the same principle, the superposition principle. And lastly, the polarization. Polarization is a special feature of a transverse wave. An electromagnetic wave, as you know, is a transverse wave. So we'll see what happens when we consider the polarization of light. Okay, now let us focus on interference. We have to add waves together by superposition principle. Once again, what is the superposition principle? It says that if I have two sources, wave source number 1 and 2. Okay, source number 1 and 2. Source 1 alone produces a certain interference, okay, which we call Y1. And source 2 alone, without any other source, would have produced an interference, would have produced a disturbance called Y2. Then what happens when source 1 and 2 are both present simultaneously? Okay, the superposition principle tells us that the actual disturbance would simply be the sum of Y1 and Y2. That is the so-called superposition principle. Okay, of course, what if you have a third source? You just add Y3. Y3 is what? Y3 is the disturbance caused by source number 3 alone, without the presence of other sources. That is the principle of superposition. Okay, now in the case of interference, once again, the sources are numerable. Say in this case, only two sources, 2-point sources. Okay, source 1 produces waves like that, source 2 produces waves like that, and you will get, under the right circumstances, you will get a pattern of alternating brightness and darkness. Okay, that is called an interference pattern. And in the case of diffraction, here's an example of diffraction. I have a slit opening from here to there. Everything else is blocked. You got a wave coming in. Okay, you got a wave coming in, and the wave would then break into tiny segments, each segment will produce its own wave traveling forward. How many of these segments are there? Not 2, not 3, but infinite numbers. Okay, infinite numbers. So here you have to use the summation. Here you have the integration. That is the difference. But it's under the same exact principle, the superposition principle. Now, let's take a look at the simplest case of adding waves up. We have only 2 waves. Okay, only adding 2 waves up. So here we have wave from source number 1 and then wave from source number 2. Wave from source number 1 travels a distance x1 before arriving at a certain spot. Wave number 2 travels a distance x2 before reaching the same spot. The total disturbance or displacement of the wave at that spot would be y1 plus y2. Okay, y1 plus y2. That is the superposition principle. Now, assuming both of these waves are sine or cosine waves, sinusoidal waves. Okay, the phase angle of this wave at that location is phi 1. The phase angle of the second wave at the same location is phi 2. And also, let's assume that they have the same amplitude arriving at that point, just for simplicity. So y1 would be a cosine theta 1, y2 would be a cosine theta 2. You can also use sine if you want to. Okay, now I take that a out. What's left is cosine theta 1 plus cosine theta 2, right? Now you know the formula, cosine alpha plus cosine beta. What's that formula? It's 2. That's the 2 here. Cosine what? Alpha minus beta over 2, and then cosine alpha plus beta over 2, right? Here is alpha minus beta over 2. Alpha is phi 1, beta is phi 2. So it's phi 1 minus phi 2 divided by 2. Phi minus phi 2 is, of course, delta phi divided by 2. And then the next one is alpha plus beta over 2. So phi 1 plus phi 2 over 2. That's phi 1 plus phi 2 over 2, of course, is the average phase, phi average. Okay, now the phase angle phi 1, as you learned from the analysis of waves, we can write it as kx minus omega t. Okay, after traveling a distance x, after time t, the phase angle is kx minus omega t, plus a certain initial phase, and that is the value of the phase angle when the wave is still here. Okay, hasn't traveled there yet. There is a certain initial phase. Okay, that applies to both of these 2 waves. So that is to say, phi 1 would be k1 x1 minus omega 1t plus phi 1 initial. And phi 2 would be k2 x2 minus omega 2t plus phi 2 initial. Right? The only thing in common between these 2 waves is the time t, because I have to add disturbances at the same moment. Okay, so t is the same. Everything else is different in principle. Now let's add them together. Right? Delta phi over 2. This is delta phi right here. And then phi average. This is phi average right here. Okay, let's take a closer look at what we got. Okay, at what we got. Look at here. Over here you have k1 x1 minus k2 x2 minus delta omega times t. See, there is a delta omega. That is the difference in the angular frequencies of these 2 waves times t, and then plus the difference in initial phase divided by 2. Alright, then followed by another cosine function. That cosine function varies as a function of time with omega. Okay, just omega. Now, in the case of visible light, omega is a very, very large value. The frequency of visible light, does anybody still recall what that is of the order of magnitude? It's 100 trillion hertz. Okay, so it varies 100 trillion times a second. There is no way we can trace any quantity that varies 100 trillion times a second. All we are seeing is some sort of time average value. Okay, that's all we can see. Now, what I'm looking for is such a case where the superposition produces a certain intensity that varies from point to point. Okay, so the intensity here may be stronger, and the next point will be weaker, and so on. But the intensity does not depend on time. It depends only on location. Okay, you will have then a distribution of intensity from point to point, and that distribution, that pattern does not change over time. It's a stable pattern. We call it an interference pattern. Okay, how do these 2 waves form a stable interference pattern? Well, let's look. Look at this function here. This function's got a omega t in there. Okay, so we look at a time average. Okay, actually, you know, to get brightness, we have to look at intensity. Okay, the perceived brightness is dependent on the intensity of light. and intensity should go like amplitude squared. This is the amplitude, okay? It should go like amplitude squared. So I have to square it. And when you square this thing, cosine squared, and you take the time average, okay? Because you can only perceive time average value. You cannot trace it 100 trillion times a second. Okay, the time average value of this cosine function equals what? Well, all these x1, x2, all these are constants. They don't change over time. The only term that changes over time is negative omega t, right? What is the time average value of a cosine omega t function squared? That equals 1/2, all right? Cosine average squared over one cycle equals 1/2. Just like sine squared equals 1/2. All right, so this term, when you take the time average, is just 1/2. Nothing else will show up. Now, look at that. Look at that term. That term is also time dependent. Okay, anything that's really time dependent, you take the time average, you're also going to get 1/2 if you square cosine. You know, what that means is that the brightness at this point has nothing to do with x1, x2. It's just some average value. Okay, so in this case, guess what? As you go from place to place to place, you do not detect any variation of intensity or variation, alternation between brightness and darkness. There is no interference pattern. What's the problem? The problem is these two waves do not have the same angular frequency. Omega 1 is not equal to omega 2, therefore delta omega, which is omega minus omega 2, is not equal to 0. But suppose omega 1 and omega 2 are equal. So what is delta omega now? 0, right? You have just killed the time-dependent part of this cosine function. All right? Now, if you square it, take the time average, it doesn't matter if you take the time average or not, because this had nothing to do with time, right? You are going to get a value of cosine squared of this quantity. This quantity can be anywhere between 0 and 1, depending on the value of k1, x1, k2, x2, and so on, right? So in that case, if for a certain location, such that k1, x1 minus k2, x2 plus the initial phase difference divided by 2, if this happens to be plus or minus 1, right? Then you square it, you get 1, which means you get the greatest possible amplitude. This will be a bright spot. Okay? On the other hand, if this quantity is such that this phase angle is 90 degrees, okay? Or, 90 degrees plus 180 degrees, whatever, then the cosine function will be 0. You square it, it's still 0, which means that location will be location of a dark spot. Okay? And that doesn't change with time. It doesn't change with time. Okay? It's stable. So, to get a stable interference pattern, we need these two waves to behave in a certain way so they are coherent. These are called coherent waves. Two waves are coherent if they satisfy what's called coherence condition. What is our first coherence condition? Well, we just learned delta omega has to equal to 0, right? Otherwise, this term is going to time average out just like the next term. Nothing will show up as a location dependent intensity, because both terms will just average to 1/2. Okay, so the first condition is omega 1 equals omega 2. Okay, if two waves want to be coherent, they have to have the same frequency or same color. In the case of visible light, they must have the same color. Okay, so basically we're saying that we're looking at monochromatic light causing an interference. Two waves with different colors will never interfere to form a stable pattern. Okay, now, is that the only condition? Well, it looks like it's the only condition, but we might have overlooked something. We might have overlooked this thing. What is delta phi initial? That is phi 1 initial minus phi 2 initial. Okay? Now, the whole idea for stable interference pattern is that this cosine, the first cosine function, cannot depend on time. I mean, the next one is already dependent on time. There's nothing we can do about it. But we don't want this cosine function to depend on time. Okay, we already killed this term, so there is no delta omega here. But what about the next term here? It is possible that if these two waves came from different sources, say here's one light bulb, here's another light bulb, it is entirely possible that their initial phases may change over time. Okay? So at one moment, the difference between two initial phases could be 90 degrees. The next moment, it could be 120 degrees. You never know. But that means that the difference in phase, initial phase, could be a random variable. I don't care whether these things are stable or not. If this guy is variable, it's a random variable over time. The time average will still get 1/2. Okay? Because it's a random function. You average the random cosine squared, you just get 1/2. All right? So there is a second condition for coherence, and that is the initial phase must differ by a constant, which is phi 1 initial minus phi 2 initial. The difference between initial phase doesn't have to be 0, but it has to be a constant, independent of time. Okay, if the two initial phases differ by 90 degrees, they should always differ by 90 degrees. You cannot have the next moment differ by 120 degrees. Okay, so these are the two coherence conditions. How do we meet these conditions? Okay, how do we meet these two conditions? Well, in the case of a sound wave, it is quite simple to meet a coherence condition between two sound waves. For example, you can have the same amplifier driving two speakers, the left speaker and right speaker. Since both speakers are driven by the same amplifier, the frequencies coming out of both speakers must be the same, and even the initial phase should be equal to each other, which means the difference between the two initial phases will simply be 0. Right? Not only is it a constant, but actually it equals 0. But things are a little bit touchy for light, for visible light. Even if these two sources are completely monochromatic of the same frequency, which means, for example, I can use a laser beam here with a certain frequency, an identical laser beam with exactly the same frequency. You have the first equation satisfied, first condition satisfied. There is no guarantee that the second condition is also satisfied. Okay? Because what determines the initial phase is when a photon is emitted. Okay? But what determines when a photon is emitted? That is a random process, right? That is determined by each individual atoms. Okay? So, what does that tell you? If the atoms here and atoms there are not the same, there is no way to guarantee that the initial phases of the wave from here and there must differ by constant. There is no such a thing. The initial phase there cannot possibly keep a constant difference from one another. This is why it is impossible to have two light bulbs, even though they're made by the same manufacturer, both 100 watts. It is impossible to see two light bulbs interfering with each other so that at a certain point away from you see, gee, it's totally dark because they kill each other. No, that never happens. Okay, for two speakers it is possible, okay, to find a spot where you hear nothing or hear something particularly strong. But with two light bulbs, two separate light bulbs, it is simply not possible. Not even with two laser beams, two separate laser beams. That is not possible. Okay, so the first condition is not that difficult to achieve, but the second condition looks like it's nearly impossible to achieve. But of course, you know there has to be a way to do that, because if there is no way to do that, there will be no such thing as interference with visible light. We wouldn't be studying this chapter, right? There must be some way. So how do we do it? Well, actually, the way we do it is quite simple and clever if you think about it. These two sources cannot be different. So what that means is that we make them the same source. Okay? We make them, so we make it such a way that source 1 and 2 came from the same exact beam. Say, same exact beam of laser. Alright? And then we just take one part of the wavefront as source 1 and another part of the same wavefront as source 2. Now if we do that, since it's the same wavefront, the initial phases must be the same or at least differ by a constant. Okay? This is how we do it. The only way to cause a stable interference pattern with visible light is if you take the same source and split it several ways. So this source 1 and source 2 really came from the same source, split into 2. You have to take the same light source and split it into 1, 2, and whatever, and then you recombine it. Okay? That is the key here. Same source, splitting apart and then recombining. This is how you satisfy the second of the two coherence conditions. Okay, so that is the central idea to satisfy the coherence condition. We take a wave, a light wave, the same light wave, split it at least 2 ways.